Okay, class, today we'll be moving on to the topic of communicating classes in Markov chains. First, let's define accessibility. For any two states, let's say X and Y, belonging to our state space script X, we say that state Y is accessible from state X if the n-step transition probability from X to Y, that is P sub XY superscript n, is greater than 0 for some non-negative integer n. We denote this relationship as x arrow y. Now, if two states x and y in script x are accessible to each other, meaning x is accessible from y and y is accessible from x, then we say these states communicate with each other. This is denoted by x left right arrow y. An important property is that communication is an equivalence relation. Let's walk through the proof. A relation on a state space script X is essentially a subset of the Cartesian product script X cross script X. Communication, as we've defined it, is indeed a relation on the state space script X, because it describes a relationship between pairs of states X and Y from script X. To prove it's an equivalence relation, we need to demonstrate three properties: reflexivity, symmetry, and transitivity. First, reflexivity. We know that the zero-step transition matrix P raised to the power 0 is the identity matrix I. This means that P sub XX superscript 0 is equal to 1, which is greater than 0 for every state X in script X. Therefore, every state communicates with itself. So, X left right arrow X. Second, symmetry. If state X communicates with state Y, that is X left right arrow Y, then by definition, X is accessible from YX arrow Y and Y is accessible from XY arrow X. This directly implies that Y communicates with XY left right arrow X. Third, transitivity. For transitivity, let's assume that X communicates with Y, X left right arrow Y, and Y communicates with ZY left right arrow Z. This means there exist non-negative integers m and n such that the m-step transition probability P sub xy superscript m is greater than 0 and the n-step transition probability P sub yz superscript n is also greater than 0. Then, using the Chapman-Kolmogorov equation, the m plus n step transition probability from x to z P sub xz superscript m plus n is the sum over all states w in script x of P sub xw superscript m times P sub wz superscript n. This sum must be greater than or equal to this single term P sub xy superscript m times P sub y's superscript n, which we know is greater than 0. This shows that X is accessible from ZX arrow Z. A similar argument can be made to show that Z is accessible from XJ arrow X. Thus, transitivity holds. So, as a reminder, since communication is an equivalence relation, it partitions the state space script X into distinct equivalence classes. And this brings us to a definition. Each equivalence class formed by this communication relation is called a communicating class. Furthermore, if we talk about a property of states, we call it a class property if for any given communicating class script C, either all states within that class script C possess the property or no state in script C possesses it. Let's reiterate the definition of a communicating class. A set of states that communicate with each other forms a communicating class. Now, within this, a communicating class script C is called closed if no transitions can lead out of this class. In other words, for all possible edges x, y, where x is in script C and y is in the complement of script C, superscript C, the one-step transition probability P sub xy is 0. Conversely, an open communicating class is one that is not closed. This means there exists at least one edge that allows the process to leave this class. That is, there exists an edge xy with x in script C and y in script C, superscript C, such that P sub xy is greater than 0. Now let's discuss irreducibility and periodicity. A Markov chain that consists of only a single communicating class is termed an irreducible Markov chain. This means that for any two states x and y in the state space script x, there exists some non-negative integer n such that the n-step transition probability P sub xy superscript n is greater than 0. In simpler terms, in an irreducible Markov chain, any state y can be reached from any state x through a sequence of transitions that all have positive probability. Next, let's define the period of a state. Let script T of x be the set of all natural numbers n such that P sub xx superscript n is greater than 0. This set represents all possible times at which the chain can return to its initial state x. The period of any state x in script x, denoted d of x, is then defined as the greatest common divisor GCD of this set script T of x. So d of x equals the GCD of the set of n in natural numbers for which P sub x superscript n is greater than 0. If P sub x superscript n is 0 for all natural numbers n, meaning the chain can never return to state x after leaving it, we define the period d of x to be infinity. A state x in script x is called aperiodic if its period d of x is 1. An important proposition states that if two states x and y communicate x left right arrow y, then their periods are equal, i.e. d of x equals d of y. This tells us that periodicity is a class property. Let's look at the proof. Consider two distinct states x and y in script x that communicate, and let m and n be natural numbers such that P sub xy superscript m times P sub x superscript n is greater than 0. Now, suppose S is an element of script T of x, which means P sub x superscript S is greater than 0. Then we can see that P sub y superscript n plus m is greater than or equal to P sub x superscript n times P sub xy superscript m, which is greater than 0. Also, P sub y superscript n plus s plus m is greater than or equal to P sub yx superscript n times P sub x superscript s times P sub xy superscript m, which is also greater than 0. From this, it follows that d of y must divide n plus m and d of y must also divide n plus s plus m. Therefore, d of y must divide their difference, which is s. Since this holds for any S in script T of X, D of Y must divide the greatest common divisor of all such S, which is D of X. So D of Y divides D of X. By a symmetrical argument, we can also show that D of X divides D of Y. Since they divide each other, it must be that D of X equals D of Y. For an irreducible chain, the period of the chain itself is defined as the common period shared by all states in that single communicating class. An irreducible Markov chain is termed aperiodic if its single communicating class is aperiodic, meaning all states have a period of 1. Here is another proposition. If the transition matrix P is aperiodic and irreducible, then there exists an integer not such that P sub xy superscript r is greater than 0 for all states x and y in script x, and for all r greater than or equal to r naught. Now let's connect this to transient and recurrent states. A key proposition is that transience and recurrence are class properties. Let's prove this. We'll start by showing that recurrence is a class property. Let X be a recurrent state and let X communicate with Yx, left, right arrow Y. This implies that there exists some positive integers m and n such that the m-step transition probability P sub xy superscript m is greater than 0, and the n-step transition probability P sub yx superscript n is also greater than 0. Because x is recurrent, we know that the sum over all s in natural numbers of P sub x superscript s is infinite. Now consider the sum over s in natural numbers of P sub E superscript m plus n plus s. This sum is greater than or equal to the sum over s in natural numbers of P sub yx superscript n times P sub xx superscript s times P sub xy superscript m. Since the sum involving P sub xx is infinite and the other two probabilities are positive constants, this entire sum is also infinite, implying y is recurrent. Conversely, if x were transient instead, then the sum over s in natural numbers of P sub xx superscript s would be finite. We can then conclude that y is also transient by observing that the sum over s in natural numbers of P sub y superscript s is less than or equal to the sum over s in natural numbers of P sub xx superscript m plus n plus s divided by the product P sub yx superscript n times P sub xy superscript m. Since the numerator sum corresponds to a shifted version of the sum for x, which is finite, and the denominator is a positive constant, this whole expression is finite, showing E is transient. As a corollary, if y is a recurrent state and there exists a state x such that y is accessible from x, y arrow x, then it must be that x is also accessible from yx arrow y. And the probability of eventually hitting y starting from x f sub xy is 1. Let's prove this. Let in script x be a recurrent state and consider a state x in script x such that y is accessible from x. We aim to show that f sub xy equals 1, which would imply that f sub xy superscript n is greater than 0 for some non-negative integer n, and thus x is accessible from y. To this end, we observe that since y is accessible from x, there must exist some non-negative integer, and such that the probability of hitting state x for the first time, starting from state y in exactly n steps, is positive. That is f sub yx superscript n, which is defined as the probability starting at yp sub y, that xn equals xn minus 1 is not x, and so on down to x1 not being x is greater than 0. This is just the probability p sub y that the first hitting time of set x tau x superscript set x comma 1 is equal to n, and this is positive. Continuing the proof, from the strong Markov property, we have that 1 minus f sub yy, which is the probability starting at yp sub y, that the first return time to y, tau x superscript set y comma 1 is infinity, is greater than or equal to the probability p sub y that tau x superscript set y comma 1 is infinity and tau x superscript. Another corollary states, let x and y be in the same communicating class and let state y be recurrent. Then the limit as n approaches infinity of the sum from k equals 1 to n of p sub xy superscript k all divided by n is equal to 1 over mu sub yy, where mu sub yy is the mean recurrence time of y. Furthermore, if state y is also a periodic, then the limit as n approaches infinity of p sub xy superscript n is equal to 1 over mu sub yy. For the proof, since y is recurrent and y communicates with x, which implies y arrow x, it follows from the previous lemma actually. The corollary, we just proved that f sub xy equals 1. From theorem 1.7 in the previous lecture, which dealt with Cesaro means of transition probabilities, it follows directly that the limit as n goes to infinity of the sum from k equals 1 to n of p sub xy superscript k divided by n is 1 over mu sub yy. Now, if y is also aperiodic, let its period d be 1. We know from general results on periodic chains, though not explicitly stated here, it's a known extension that if it's a periodic and recurrent, the individual probabilities converge. Specifically, there exists a positive integer r naught such that for all n greater than or equal to r naught, p sub y I superscript n d, which is just p sub y I superscript n since d equals 1, is greater than 0. The stronger result for aperiodic positive recurrent chains is that the limit of p sub xy superscript n itself is 1 by mu sub yy. We now arrive at a central theorem. The states in any given communicating class are all of the same type. That is, they are either all transient or they are all null recurrent or they are all positive recurrent. To prove this, it's sufficient to show that if x and y belong to the same communicating class and y is null recurrent, then x must also be null recurrent. We've already shown transience and recurrence are class properties. So let's take r and s as natural numbers such that p sub yx superscript r times p sub xy superscript s is greater than 0, which is possible because they communicate. It follows that p sub y to the power r plus e L plus S is greater than or equal to P sub Yx superscript R times P sub X superscript EL L times P sub XY superscript S for all natural numbers EL. Therefore, for any n greater than R plus S, we can write the Cesaro sum for state Y as 1 over n times the sum from K equals 1 to n of P sub Y superscript K is greater than or equal to 1 over n times the sum from K equals R plus S plus 1 to n of P sub Y superscript. This in turn is greater than or equal to the term n minus R minus S over n times 1 over n minus R minus S times the sum from EL equals 1 to n minus R minus S of P sub XX superscript EL times P sub YX superscript R times P sub XY superscript S. Since Y is null recurrent, the left hand side, the Cesaro sum for Y goes to 0 as n increases. For this inequality to hold, given that P sub X superscript R and P sub XY superscript S are positive constants and n minus R minus S by n approaches 1, it implies that the limit as n goes to infinity of 1 over n times the sum from EL equals 1 to n of P sub X superscript EL must be 0. This is precisely the condition for X to be null recurrent. Hence, X is null recurrent as well. This completes our discussion for today on communicating classes and their fundamental properties.